So by the end of this lecture, you'll be able to understand the mechanisms of entropy transfer and also apply entropy balance equation in closed systems, apply the entropy balance equation in open systems. If you want further reading or need to expand your knowledge horizon, you can always go through the reading list that you see here in the recommended text. Okay, so this equation we are familiar already because we discussed this a bit in the previous lecture. Entropy balance, right? So entropy balance is comprised of entropy coming into the system and minus the entropy going out of the system plus the entropy generation inside the system, right? So for entropy to come into the system, there are two mechanisms. Either it can come with heat or mass, right? So if it is an open system, entropy can enter to the system with the entering mass. But if it is a closed system, then we don't have mass flowing in or out of the system. Therefore, mass component does not need to be considered in closed systems, right? So similarly, entropy can be leaving the system with heat or mass leaving the system. In addition to these two mechanisms, you know that due to irreversibilities, entropy can be generated inside the system. So when we have irreversibilities, entropy generation or Sgen is greater than 0. And when we don't have irreversibilities, Sgen is 0. For a reversible process, in a nutshell, for a reversible process, there's no Sgen. Sgen goes to 0, right? And importantly, energy is transferred by work, right? But entropy is not transferred by work. So in the previous cases, enthalpy, internal energy, we related that with the work. But irrespective of whether work is being done or done on the system, entropy level does not change. It might change the heat input output, but entropy level does not change. Based on that, it does not contribute. To be precise, work does not contribute to the entropy balance equation. So are we clear up to this point? This is kind of a summary of yesterday's discussion. Are we clear? Anyone having challenges up to this point? I really appreciate if you can be involved in the chat because this lecture is kind of with including a lot of details. W won't affect delta S. No, W has nothing to do with delta S, but you know from the first law, W may change the amount of heat transferred in and out of the system. So it can affect the heat. So with the change of heat, entropy can change, but W directly does not do anything in the entropy balance equation. Okay, so let's move on. You remember to remember in order to calculate the entropy change or entropy coming in and out, going out of the system due to heat, we introduced this integral, right? So we said the entropy change due to heat transfer can be written as delta Q over T, right? For a reversible process, right? And similarly, like in the same discussion, we said if the temperature that we are dealing with, Tk value that you see here, temperature that we are dealing with is a constant. If it is a constant, then we can take this T out of the integral. Therefore, we can write it as a summation. For an example, let's say in this bottom right hand corner, we see a figure, right? We have a heat input, like let's name it Q1, this one Q1, and then we have heat output, let's say Q2. And the outside temperature, let's say TA, right? So if we want to do this for such a situation, assuming that the atmospheric temperature does not change for these given conditions, we can say that Q1 is a heat input, right? Heat input is always positive. Then we say Q1 divided by TA minus, because Q2 is leaving the system, minus Q2 divided by TA again, right? So do you understand why we cannot use this simplification to represent the integral that we see here if temperature is varying? If the temperature is varying, can we use this simplification? We cannot, right? That because like if it is a constant on, then only we can take it out of the integral and make the equation look like this. So we'll be using this equation a lot because in many examples, in many situations, we'll have a temperature constant at the outside. So we'll be using this relationship, right? It's not only two heat transfers. Let's say we had Q3, 4, 5, 6, whatever, n number of heat components going in and coming out. Still, we'll extend this equation as seen here. As we just did for these two, we can do it for many. It doesn't matter, right? So the next point says what I just said. If TK varies, this approximation cannot be done, right? And then the most challenging part for many students in these entropy calculations is finding the TK value. What should we use to find the temperature? Please pay attention to this one very closely, because this is simple, yet if you do not get it right now, then maybe you will be confused when you're trying to solve the questions, right? So entropy generation, right? Entropy generation, is it done inside the system and or outside the system, or done inside and outside both of the system, like inside and outside of the system, both? Can somebody answer this question? Entropy generation, is it limited to inside of the system, like inside boundary? Let's say in this case, like we define a boundary like this in the bottom right hand corner, we define a boundary like that. Or this boundary and outside entropy generation can happen in inside and outside both, or outside only. So there are three possibilities. What can you say about that? Any idea? Not exactly. Entropy generation happens um, inside and outside. So to give you some perspective, when we are doing some process, when we are doing some process, the process impacts the system and the surroundings, right? It impacts both, right? So if it is a reversible process, then it doesn't affect anything. So if it is specifically said it's internally reversible, it does not have anything to do with inside, it's only outside. So for this course, any reversible process can affect both surroundings and system, unless we find out that it's not doing so after subsequent calculations. Are we clear about that? Entropy generation can happen inside and outside of the system. Perfect. Now, if we wanted to find, let's say, the entropy generation inside the system, let's call it SDN1, right? So entropy generation inside the system. So entropy generation outside the system, let's call it SDN2, right? Now, if we want to find the total entropy change, total entropy generation, sorry, total entropy generation during this process, what would that be? Is it 1, is it 2, or is it 1 plus 2? Any ideas? It's 1 plus 2. Excellent. So because we have some entropy generation inside the system, some entropy generation outside the system, so it's going to be the total of these two, the total entropy generation, as the name implies, right? And when we want to find SGN1, then we use the boundary temperature of the inside system, like the one indicated in red color, right? The system boundary, this boundary. If we want to find SGN1, then we use that temperature, right? So if we want to find um, the total entropy generation, SGN1 plus SGN2, then we use TA, atmospheric temperature. If we use that, then we are getting the total entropy generation, basically SGN1 plus SGN2. Okay, do we make sense? Now, do you know how to pick the appropriate T value, temperature value? If we want to find SGN1, then we pick TB, the boundary temperature of the system, right? If we want to find the total entropy generation, SGN1 plus SGN2, basically total entropy generation, then we use TA, outside temperature. Are we clear on what temperature to use in these two instances? Perfect. So now this is the principle that we are using, but we'll see in the examples that how this is being applied. Okay. So we can use first law to find for a closed system. We know that this is our first law equation for a closed system. We can use this to find the heat transfer values, right? Um, and then we plug in those heat transfer values as discussed in this equation. So you see that we need our good old friend first law even in entropy analysis, right? So we cannot forget about that. So it is needed here as well. Now, you remember we learned the entropy generation equation for a closed system yesterday as well. So total entropy change of a system, entropy change is equal to entropy transferred by heat coming in and going out of the system, and also entropy generation. And this one is a simplification of the integral that you see earlier, right? And if we want to solve questions, then we cannot solely solve everything based on this equation. We might need to combine this with the first law principles, thermodynamic tables, or ideal gas assumptions as necessary. Okay, so is there anything that is not clear up to this point? This is kind of a summary of what we did yesterday. Is there anything not clear, or are we clear? Are we good to move to the next slide? Are we clear on this one? Perfect. Let's move on. So this slide is also from yesterday. So for solids, we can use C into natural log of T2 over T1 as to find the entropy change of a solid or a liquid. You know that for solids or liquids, the CV and CP equals C, one value, right? For solids and liquids. This does not apply. This relationship cannot be written as this for gases or vapors. And then you remember we learned there's a method one that we can use to calculate the entropy change of an ideal gas. But this method one will not be tested in exam. Okay, this method will not be tested in exam. So this is just for your knowledge. And the method that we are going to use very commonly in our course, in this course, is these two equations, right? So when we are using this equation, you can use either of these to analyze the entropy change of an ideal gas during a given process. So depending on the parameters that is given in the problem, we'll pick one of these two equations. If we have temperature values and pressure values given, then this equation just need temperature and pressure, right? It does not require us to find the specific volume. So if we know temperature and pressure already, then it's a good idea to go with that equation, right? The second equation, if we have temperature and specific volume information, then we go with the second equation. So both these equations produce the same answer. It's just a matter of convenience. If we have the parameters that is needed for one equation, then we'll go with that because that's easier to do, right? So are we clear? So entropy change in a non-ideal situation, it's always going to go with the tables, right? So if you want to find S2 and S1, then it's similar to the previous cases. When we don't have the ideal gas behavior, then we look into the tables. That's our only resort. Yeah, so this is specific entropy change. That's a very good observation, Alan. So if we want to find the total entropy change in the sense of like including the mass, not specific entropy change, then we have to multiply this entire equation by the system mass. Okay. Did I answer you both? Okay. Awesome. So now it's time to get our hands dirty and do some real work. So work on this one. Take 5 minutes. Try to solve this question. When you are trying to solve this question, use please note that the surface temperature and outside air temperature is given, right? So how much entropy is generated in the chip? Think about the concept that we discussed. What temperature to use when you want to calculate the entropy generated in the chip, and how much is generated outside the chip? Then think of what temperature has to be used. What is the total entropy generation? Think of what temperature has to be used, right? So in these kind of questions, you may see some unnecessary details. Maybe all the details are necessary. So be careful when you don't just plug in the numbers like crazy, because I have done that as well. So I have seen it in some of the answer scripts. So you write a long answer, but still we could not find a place to give you a mark because you were just plugging in the numbers without thinking too much. So don't do it. Don't repeat that mistake again in the coming quizzes or the finals. Stop when you read the question and think about the situation. Think of the problem. Use your thermodynamics knowledge and then plug in the numbers. Okay. Okay. Take 5 minutes to attend this one. Okay, so let's start discussing this question. So this question discusses about a computer chip which dissipates 2 kilograms of electric work over time, right? So when we look into this as a um, closed system, because the chip mass of the chip is not going to change, then we can apply the first law equation for the for a closed system, right? So delta U equals Q minus W, right? So in this case, there's no internal energy change. We have to assume the steady state operation, because otherwise, if the chip keeps on heating, then it's going to burn itself. Therefore, we can assume that the temperature is not changing. Then delta U is 0, right? Delta U is 0. So with that, we can say that Q equals W. Therefore, the W value is given here. So we can bring that up. So 2 kilojoules. So now we have already found the heat that is transferred by the chip, right? And then after finding that information, then what we are going to do is we need to find um, the entropy generated in the chip, right? So let's take a cross section of the chip like this here. Uh, let's assume this is the chip temperature on this surface. It's going to be 50 Celsius. And we'll think of another system boundary. The immediate air layer, right? So in this layer, the outside temperature is going to be 25 Celsius, right? This is a simplified way of looking at the chip, but the chip is a 3D one, but I have just drawn a 2D representation of this thing. So the heat crosses the boundary like this. So are we all clear up to this point, including the surface temperatures and how we found the heat? Anybody? Can you answer? Are we familiar up to this point? Why change in the entropy is zero? We have not come to entropy change. We have discussed about internal energy change, and we have calculated uh, the heat transfer. Because assuming steady state conditions, then we can say that the chip internal energy is not changing. Did I answer your question, Alan? All right. So now let's try to write the entropy equation for the chip, right? Let's name the chip as system 1, and the surrounding as system 2, immediate air layer outside the chip, right? For system 1, sys 1, we can say that delta S equals Q over we'll start with this one. Now we have found the temperature, so found the heat, so I'll erase this one so that I have more space to start with. Okay, now let's start from here. Sys 1 delta S is equal to integral of delta Q over temperature plus Sgen. For steady state conditions, what can you say about delta S? Any idea? For if we assume steady state assumptions, what can you say about delta S? Excellent. Because entropy is a state property. If it is if the system is in steady state, then this is going to be zero steady state assumptions. Right? So with that, we can say that 0 equals, and with this one, if we want to find the temperature, if we want to find the entropy change in the chip, what temperature should we use? 50 Celsius, 25 Celsius? What should we use? We are interested in system 1, which is the chip, right? So what temperature should we consider? Anybody? Excellent. Because we want to find the entropy generated inside the system. You remember in the last few slides we discussed what temperature to pick, right? If you want to find the entropy generation inside the system, then we pick the system boundary temperature of the system. So therefore we can say that it's 50 and it's not going to change. Therefore we can pick 50 and plug it in there. And then the Q value, we have 2 kilojoules generated, and heat is leaving the chip, right? Heat is leaving the chip. So that means we can say it's going to be -2 divided by temperature, very important, 50 plus 273.15, because we need to convert it to Kelvin, plus Sgen, right? So now we can find our entropy generation from this uh, portion. Any questions so far? Any questions? Anything not clear, or are we clear up to this point? Negative sign came because the heat is leaving the chip, right? That's why we have the negative sign. Does it make sense? Okay. Are we clear now about this portion? Yes, in this course, it's fair to assume steady state operations because we are not dealing with transient systems. We can assume steady state operations. Okay. So are we clear now? Anybody having more questions? That's always good to ask questions if you have any. Okay, I see none. I assume that all of you are familiar. Now we have found the entropy generated inside the system, right? Now it says to find the entropy generated outside the system. Okay. Now how are we going to do that? Now let's assume our immediate surrounding, the air layer. Let's take our immediate air layer, right? This is a 3D space, but I'm just drawing it as a box. Let's say this, let's say this dark blue area, the dark area that I am painting right now, is the surface that is contacted with the chip, right? So from the chip, we receive Q1, and from the outside boundary of this air layer, we leave Q2, right? Under steady state assumptions, we can say that if we use the first law equation, assuming this to be assuming there's no mass transfer, so we can say that Q1 should leave the system. So Q1 should be equal to Q2. Otherwise, the temperature in around the chip is going to increase. Therefore, the chip temperature is going to increase. Do you all agree with this notion? Q1 equals Q2. Perfect. Now, with this one in hand, we can calculate the entropy change in this system 2, right? For system 2, we can say that 2, then delta S equals, again, the temperatures are not going to change, so we can use this form, sigma Q over T plus Sj, right? And here, for steady state assumptions, this goes to 0. And then we can say that 0 equals Q1 is coming into the system, Q1. And what is the temperature of that surface? Q1. What should we divide Q1 with? Is it 50 or 25? It is 50, right? Because the dark blue boundary is the surface that we are connected, the chip surface and the air layer, immediate air layer. So this one is at 50 Celsius. So we have to put 50. And importantly, 50 plus 273.15. And it is coming into the system. Therefore, it is going to be a positive entity, right? And then Q2 is going to be divided by Q2 is going to be negative because it's leaving the system, and the temperature is going to be the temperature is at this outside boundary, right? At this boundary, that is going to be the ambient air temperature, right? 25 Celsius, right? So we pick 25 plus 273.15. Don't worry about writing this one, please listen to me, right? Because at this point, I have the solution in the other page. I'm working on with you so that we get more understanding. Okay, and then simply plus Sgen. Here we have Q1 and Q2. The magnitudes are equal to 2 kilojoules. So we have everything we need to find the entropy generation inside and outside the system. We just found the entropy generation outside the system. Is there any confusions, questions about this portion? Are we clear? Perfect. So let's, if we need to find the total entropy generation, what can we do? We can get Sgen 1 and Sgen 2 and simply add these two, right? And there's another method to find Sgen total entropy generation. We'll discuss it in the coming slide with the answer, right? So if we go through the solution process again, so here this line is similar to what we did. It finds out that electrical work is equal to heat transfer, right? And then in the entropy generation equation, so this goes to 0 according to steady state assumptions, and then we can say that it's then in the first portion, SGN inside the chip, right? So that is going to be 6.19. After that, we define a new control volume in the chip surface, and there again the internal energy change is 0, and therefore we can say that there's no work done because the outside air layer has no boundary work or any other means of doing work. Therefore Q1 equals Q2, and then we apply the entropy balance equation assuming steady state assumptions. Therefore this becomes 0, and we apply the entropy balance equation to find entropy generation in the control volume 2, like this. And then we add those two up to find the total entropy generation. Okay, now we'll answer the questions. So change in U and change in S are all 0 because of steady state conditions. Yes, if it was not steady, then we cannot assume this to be having like different U values, right? In certain questions, like the internal, if the temperature and conditions are changing, like then we cannot assume this. We'll come across one or two questions like that, but we are not wanting you to evaluate the transient conditions. But in this case, in this course, you will have situations where entropy change and internal energy change are not 0. You remember you already encountered with situations where internal energy is not equal to 0, the change of internal energy, right? Awesome. So now we found out this is our total entropy generation. So is there a shorter way of doing this? You remember in the first theory section that we discussed today, I said if you want to find the total entropy generation at once, then there's a way to do it, right? So total entropy generation, then delta S of the system equals Q divided by T surrounding T surrounding plus Sj. So Q is leaving the system in this case. This is minus 2 divided by 25 plus 273. Delta S equals 0 assuming steady state assumptions. Therefore this becomes Sj, then becomes plus. Can somebody check the number that we get with this one? Two divided by 25 plus 273 kelvins. 0.0067. Excellent, Ryan. So 0.0067 kilojoules per Kelvin. So if we convert it to joules per Kelvin, it's going to be 6.7 joules per Kelvin. What a coincidence. Can you see this one? So it's not a coincidence, it's how it is done. If you look at these two equations, Sj in this one and this portion, let me circle it in red. This is the total entropy generation in the system, right? So if we add these two up, these two are going to cancel out, right? That's why we get the same answer for total entropy generation if we just divide the heat transfer by the surrounding temperature. So are we clear about this process? Which temperature to use and the assumptions underlying this question? Perfect. Menna, to go back to your question about is it always fair to assume steady state? It There are instances where it is not fair to assume that, right? If the properties of the system are changing, it's not fair. But I made a wrong statement. We don't deal with such situations. In certain questions, you have seen that internal energy change, right? So in such situations, it's not a steady state system. Okay, are we clear about that? Okay, perfect. All right, if we have no questions about this one, then we'll try the second question. Take 5 minutes and try to solve this one. Okay, has anyone managed to complete the solution already? Okay, let's go through it together. This says saturated water vapor at 200 kilopascal. So does it contain enough information to find the properties at this point? Saturated water vapor at 200 kilopascals. Can we find the required information using this one? The state properties, the entropy, enthalpy, and everything? Anybody? We can, right? Saturated water vapor. So basically, what it says is, if you look at this one, let's say PV or something, and then if we mark the DOM, what it says is our state is this one, right? So then we can get the VG values, UG values, SG values, HG values, and everything as our state properties, right? So we have enough information to define our state one. Yes, it is on the vapor, saturated vapor line. Therefore, we have all the information required to define state one. State one, let's say it's done, right? We can find anything we want. And now it says that it is compressed to 600 kilopascals. This is at 200 kilopascals, and state 2 is at 600 kilopascals. Okay, and it says reversible. What does that say? When we see the word reversible, what does that mean to us from a quantifiable parameter point of view? Does it make anything different? Does it make something zero? Perfect. Sgen is zero, right? Because Sgen is a representation of the irreversibility, and if there's no irreversibilities, then Sgen is equal to zero. In this process, there's no entropy change. So basically, what does that mean? Okay, let me stay there for a bit. And then it says adiabatic. What does that mean? Adiabatic? Anyone? Excellent, Isra. So Q equals zero, right? So with this one, if we write the entropy change equation, delta S equals, for a closed system, Q over T plus delta Q over T plus S gen. From our reversible assumption, we can say that this is zero, right? And as this is adiabatic, Q is going to be zero. So 0 divided by anything and integrated doesn't really matter. So it's going to be a 0. So now from this one, we can say that S2 minus S1 equals 0, or in other words, S2 equals S1. Is that all good? Do we all agree up to this point? Awesome. So now we agreed that we can find all the properties related to state 1, right? We have the pressure at state 2, and also it seems entropy at state 2 is same as S1. Therefore, we have entropy at state 2 as well. So to define state 2, we have the entropy and the pressure. So does that mean we can find the specific volume and temperature at that given state 2? Do we have enough information to find those? Perfect. We have enough information. You remember we had similar instances, right? When we knew the enthalpy, then with the pressure or temperature, then we were able to find the required information, right? So let's move into the solution now. So it just discusses the assumptions first, adiabatic and reversible. So therefore, this have become 0, and from the entropy change equation, entropy balance equation, we say that the entropy is constant, which essentially means S1 is equal to S2, and as the state 1 is on the saturated vapor line, as we discussed earlier, here we can find all the properties by looking at the two-phase tables. We go to two-phase table, and as this is water, we have pressure and temperature entry both, and it's easy to pick pressure entry in this case. So we go to 200 kilopascals, and we record specific volume, internal energy, specific volume, entropy, and temperature. We can record everything. We can also find internal energy, enthalpy if needed. Okay, and after that, we know that at state 2, again, the entropy is going to be the same number. So S1 is 7.12. So we can go to property table. Let's do it together. So let's go to two-phase tables, saturated water, and we'll go to pressure entry. Okay, now we are at pressure entry, and our interested pressure at state 2 is 600 kilopascals, right? 600 kilopascals, and this table does not have the entropy, so we have to go further down to, yeah, this table has entropy and 600, and our entropy columns are the last three, so we can check our entropy value. Entropy value is 7.1271. Okay, so if you go there, you can see for 600 kilopascals we don't have 7.12, right? It is higher than our SG value for 600 kilopascals. Therefore, what does that mean? Our entropy value is higher than SG value. So we are in superheated region. Therefore, we have to go to superheated tables and find the relevant entropy value. Yeah, sure. So at state 2, we know the pressure and entropy, right? We are clear up to that point, okay? And then we take this number to our property table, and our property table, like, we go for the pressure entry table as it's convenient as of now, and we locate 600 kilopascal, and the last three columns of our this table is about SF, SFG, and SG, and then our entropy value is 7.1, which is higher than SG value. So that essentially means that we have to look into the superheated tables to find our entropy value under this given pressure, because it's out of our region. Okay, so now we go to superheated tables, superheated water tables, and now we have to locate our pressure, 300, 400, 600, and in this 600 table, so entropy is the last column, and there our required one is, let me check the number, 7.12 So 7.12 should be in between 6.9 and 7.18, right? So our interested entropy value is within this bracket. Therefore, we can do interpolation to find the required properties, specific volume and specific volume and temperature, right? That is what is being done here. Are we all clear? Are we all clear? Or any questions so far? Anybody having doubts, questions, needing more clarifications? Perfect. So now let's look into the next question. Take a few minutes and try to solve this one. Okay, so in this discussion or this question, it says there are two 5 kilogram blocks of steel, one at 250 Celsius, the other one at 25 Celsius. So this is, let's say, TA equals 250 Celsius and TB equals 25 Celsius, right? And then it says they came into thermal contact. And what can you say what happens if they were in thermal contact? A high temperature block and a low temperature block, then what would happen? What would be the what would happen to the temperature of the two blocks? Would it come to a common temperature after a while, somewhere in between 25 and 250, or would it increase or would it decrease totally? What would happen? Any suggestions? It will come to a common T, and it will be in between 25 and 250 Celsius. Excellent, Lisa. So now, then find the temperature and the total entropy generation in the process if the outside surfaces of the blocks are insulated. Right now, it says outside the uh, outside these blocks, there's no heat transfer. That is what we mean by insulated, right? So if we want to find the final temperature, we can try with the first law for a closed system. If we think of this as our system boundary, A plus B, right, the total block, we can write the first law equation, delta U equals Q minus W. What can you say about Q? What can you say about Q? Is it 0 or does it have a value? We are applying the first law equation to A plus B. Anybody? Is Q 0 or does it have another value? It's going to be 0 because it says well insulated, right? So it's going to be 0. And what can you say about W? Is it 0 or does it have a value? No, it does not, because we have to think from the first basics, right? So does it have a boundary work? Does it have electricity or something coming in or going out? No, nothing. So there's no work. That's why we say W is equal to 0, right? And now it leaves us that the internal energy of the system does not change. The total internal energy of the system does not change from state 1, like this is at state 1, right? This is the initial condition. This is 1. And at the final conditions, both blocks come, uh, let's say these are TA1, TB2, 2 plus TB2 equals T2, the common temperature that we were discussing at the beginning of the question, right? So now both blocks should be in the same temperature at the end of the process, right? So if we apply, we know that the internal energy change can of a solid can be written as delta U equals mCV delta T. So CV or C doesn't matter because this is a solid. Therefore, for solids, you know that CV equals CP equals C for solids, right? So doesn't matter if you put CV or not. And so you can find delta UA using delta TA, right? And this is for block A. And you can also do the same thing for block B and say that mCV delta TB, right? Now the total is going to be equal to delta U A plus delta U B equals 0. Do we make sense here? Or anything not clear up to this step? Anything not clear? This should be MA. Anything that is not clear, or everybody is getting perfectly fine? Perfect. Now from this equation we can find the T2, right? So if I write this one from this relationship, we know that we can write MAC T2 minus TA1. Similarly, we can say that MBC T2 minus TB1. TA1 and TB1 are known already. It's given to be 250 Celsius and 25 Celsius. And MA and MB are known. These are the same weight, 5 kilograms. And C is not going to change for these two blocks because it's both made of the same substance, steel. Therefore, from this equation, we can find T2, right? Anybody that is not clear about that portion? Or are we 100% clear? Everybody can find T2. This is not even entropy. This is the knowledge before the second law. This is first law knowledge. Okay, I assume all of us can find that one. Now, after that, our goal is to find um, the entropy generation. Total entropy generation in the process, right? So how do we find this one? So we can write the entropy equation delta S equals uh, integral of delta Q over T plus S gen, right? So we know that this one is 0 because there's no heat transfer with the outside environment because it's well insulated. Therefore, so we can find Sj by delta S A plus delta S B equals S gen, which means M into S2 minus, oh sorry, to find this one it's a solid, so we can find delta S using C MC log T2 over T1, the temperature ratio. So you can find delta SA and SB using this equation. Okay, anything not clear so far? Anything not clear so far? It would be really nice if you can be involved in the chat. If you get it, you get it. If you don't get it, you don't get it. So please involve. Thank you, Desa. So now let's look at the solution. So this portion discusses the internal energy balance that we discussed. So from that one, from the first law, they found the final temperature, and then from this equation, as we discussed earlier, for considering the entropy change of block A and block B, they have found the total entropy generation during the process. Okay, and it's important to note. Sorry, it's important to note that we did not use here. We did not try to do something like sig delta Q over T. This simplification. It's anyway like no heat transfer with the surroundings. But even if the surroundings had a heat transfer, the temperatures of the blocks are changing and everything is changing. But if and only if the temperature here is constant, we can use it, right? If we wanted to find the total entropy generation within the system, could we have used this relationship, total entropy generation within the system? Could we have used this relationship, this simplification? If we wanted to find the internal entropy generation, then we'll have to pick this blue color boundary as I am just drawing now, right? So, but the temperature of this boundary is constantly changing because the blocks are changing the temperatures, right? Therefore, for internal conditions, we could not have used this relationship that we see here. But if the atmospheric temperature T surrounding, sorry, TA is confusing. Let's say T surrounding was given to be a constant value, can we use this simplification, the very same simplification, to find total entropy generation? Can we do that? Not total entropy generation, like to find the entropy change due to heat transfer. Can we do that? Anybody? Can you guys hear me? Awesome. So what I'm saying is, if we have a boundary temperature that is changing, still, if the surrounding temperature is not changing, and we wanted to find the total entropy generation of during the process, then we could have used surrounding temperature. Not in this case because this is insulated, but there will be no heat transfer to the outside. But if we had heat transfer to the outside, then we could have used the surrounding temperature and still found the total entropy generation during the process. Does it make sense? Awesome. All right. Let's look into example 4. Do you need a break or are we good to continue? Good. Okay, so take 5 minutes break and take another 5 minutes to try this question. So we'll meet in 10 minutes. Okay. So are we all back? When we consider two systems and there is steady state flow, is delta is always zero. So we cannot say that there are two systems and delta is always zero. It depends on the context, right? So in the first example, the chip was operating in a steady state condition, right? So most of the devices, to correct my previous statement, the devices that we evaluate in this course are steady state devices mostly, right? So the chip that we discussed, it generates 2 kilojoules constantly, but it does not change its states. Then we can assume steady state assumptions. Did I answer your question, Lisa? Saying always steady state, that's kind of an overkill. Yeah. Okay. Now let's start with this question. It says a Carnot cycle heat engine with water as the working fluid. So our substance is water. So we know that water is there. Water. Easy. And when we see water, the first thought that should come into our heads is we cannot use ideal gas. So we have to look into property tables, right? And then heat transfer to the water occurs at 300 Celsius. So heat transfer to the water. Okay. So this is 300 plus 273 Kelvin. So this is high temperature reservoir. And then we have our heat engine, and it absorbs heat, which is QH. And then it emits some heat into rejected from the water at 40 Celsius. It ejects the heat into 40 plus 273 Kelvin. 273 Kelvin, right? And that is QL. And while doing so, we deliver some work out. And again, there's an interesting, important notion. During the heat transfer process, the water changes from saturated liquid to saturated vapor. So this is very important. So we were asked to draw this cycle on a TS diagram, S, T, and similar to the previous cases, we have the dome, and the heat transfer process, it says, happens from saturated liquid to saturated vapor, right? The temperature is 300 Celsius, right? Let's call this 1 and let's call this 2, state 2. So, isothermal, from Carnot heat cycle, we know that the heat addition is isothermal, therefore the temperature is going to be constant, and it says the heat transfer started at saturated liquid state and then it heats the substance until we reach saturated vapor. So are we clear up to this point? Perfect. Now it says the heat is rejected from the water at 40 Celsius. So we know that heat rejection should happen at 40 Celsius. I will not mention Celsius all the time, then it's kind of confusing. Instead, I'll put it at the top. right? And then now we have 40. And the second process after heat addition, then we have uh, expansion through the turbine, right? The work output phase. And any process that is involved in this discussion is either any process involved in this one is reversible, right? A reversible work transfer has no entropy change, right? So therefore, from state 2 to 3, we should come on a straight line. I'm sorry if it's not like one. 2 to 3, state 3. Are we clear about the state 3? Are we clear about the state 3? How we came across? Why this line is vertical? Perfect. Now from 3 to 4, we have isothermal heat rejection. From 3 to 4, we have isothermal heat rejection. And 4 to 1 is again an isentropic compression. So if there's no entropy change from 4 to 1, this portion should be again vertical. So 4 is here. Now are we clear about how we develop this TS diagram? Any questions on that? Okay. So from our previous class, we know that eta thermal of a heat engine can be written as the desired output, which is the work, and the required input, which is QH. For a Carnot heat engine, we can write the same as 1 minus TL over H, right? So one question that we have been asked in this process is the thermal efficiency. The thermal efficiency can be found using this equation easily, right? Can we do that? Okay. So then the other question that is being asked from us is the work transfer, work done during the process, right? So in order for us to do that, we need to find the 4 states, the properties at 4 states, okay? And finding state 1 is pretty easy and straightforward because it says the temperature is 300 Celsius and it is on the saturated liquid line. So basically we have to go to temperature into tables of water and we can grab VF, HF, UF, SF, everything related to the saturated liquid line, right? Similarly, state 2 is going to be on saturated vapor line where the temperature is 300 Celsius again. So we go to temperature entry tables and we locate this one, this temperature, and then we get VG, HG, UG, SG. So all the parameters, right? And then we know that S1 equals S4 and S2 equals S3. Can we agree upon that? S1, S2. So the same number goes for S3 and S4, right? So based on this, as we already have S1 and S2 in hand, then we have S4 and S3 in hand as well, right? We have been asked to find the quality at the beginning and end of the heat rejection process, okay? So quality needed to be fine. X equals S minus SF over SFG, right? So you remember from the last class, we said we can relate the entropy with the quality as this. So we know that entropy at state 3 and 4, right? So for each state, we can substitute for S using S3 or S4, depending on the state. And then SF and SFG is the entropy values at 40 Celsius from your two-phase diagram, two-phase table. Can you all find X using the information that we have so far? Can we all do that? Can you explain? 2 to 3. Yes, of course. So in a reversible, let's say this is a heat engine, right? So let's assume this is a turbine. So if it is a reversible turbine, then there are no irreversibilities, no entropy generation, and at the same time, no heat transfer in the process. Therefore, no entropy change. Does it make sense? This is the way Carnot cycle is being defined, right? Reversible isothermal heat addition is 1 to 2, and then 2 to 3 isentropic expansion, and likewise, right? So if you go to the previous lecture, the definitions are there. So now you see how it relates to our questions, right? So this is very important, because when we see the definitions, it doesn't really make much of a significance there, but when it comes to problem solving, it brings in some value. Okay, now let's go into the solution. So as we discussed earlier, x3, x4 can be found, right? And then thermal efficiency. So for Carnot engines, S1 equals S2. No, S1 and S2 are different because these two are here, right? 1 and 2. Entropy generation is always 0. S1 and S4 are equal, yeah. And for any process in Carnot engine, entropy generation is 0 because all the processes are reversible. Okay. And now we are clear up to finding x3 and x4, right? Anybody having trouble with that? Or can we all find the quality? Anybody who's clear about finding the quality? Anybody who has no doubts? Perfect. And are we all clear about finding the Carnot efficiency? Perfect. So to find QH, like from process 1 to 2, process 1 to 2, let's say delta S equals Q over T plus Sgen. But for a Carnot cycle, we know that any process, the entropy generation is 0. Why? Because all the processes are reversible, right? And then this is an isothermal heat addition. Therefore, we can say that this is equal to QH over T. From this relationship, we come here to find the heat addition, the total heat input to the substance. Is that step clear? Or any doubts up to this point now? Any challenges of that step? We applied the entropy balancing equation to process 1 to 2. Yes, we said that for saturated vapor, quality equals 1. For saturated liquids, quality equals 0. So we did not find the quality for state 1 or 2. So in that case, your argument would be valid. But state 3 and 4 are not in saturated vapor line or saturated liquid line. Did I answer your question, Menna? Perfect. So yes, QC leaves the system, but we wanted to find QH, and that's why we just picked state process 1 to 2. Considering process 1 to 2, this is the heat exchanger, right? Which received the heat. Okay, does it make sense? All good? For steady states, we did not assume to be assumed Q equals 0 anywhere. The steady state has nothing to do with Q. Okay. Okay. Because like without a heat input, a device cannot work. Sgen is 0 because all the processes involved in Carnot heat engine are reversible. For any reversible process, Sgen is equal to 0. Okay. So everybody clear about how we quantified QH? Any questions on that one as well? Or are we clear? Perfect. After finding QH, it's a pretty straightforward process. Now we have the thermal efficiency, and we know that relationship between thermal efficiency QH and W net. And what we need to find is the W net. So we can multiply the thermal efficiency by QH to find the W net value. So we come at the final answer. Okay. So I hope the last step is straightforward. If you have any questions, I'll give you 2 seconds to ask, 2 3 seconds, because we are running out of time. If you have questions, we can answer. Do you have any questions? All clear? If you are clear, please put a thumbs up. Then we can move on to the next question. Perfect. Now, take about 2 3 minutes to go through this question. Okay, let's go through the solution process together. So it says compression and heat transfer brings R134A. So this is the substance we are dealing with, R134A. And I want to emphasize one thing. When you see R134A, never look for ideal gas assumptions. Always look for the tables. So this mistake have been done by you in the midterm, but we did not penalize you on that regard. We deduct few marks on using that ideal gas assumption, but then we gave marks for the process. But that would not happen in the next exam, right? So learn from the mistakes that done in the midterm, and don't ever use ideal gas assumptions for R134A. Okay, it's a refrigerant, and it doesn't necessarily say that it's a gas. So we don't know whether it's a gas or a liquid or anything. So it could be in any state. So don't use that assumption. Okay. All right. So R134A initially was at state 1, it was at 500 kilopascals and 50 Celsius. And then compression and heat transfer brings it to state 2. So it says it become a saturated vapor at 50 Celsius, because the process is isothermal. The question says it becomes a saturated vapor following an isothermal process, right? So now saturated vapor at 50 Celsius. Find the specific heat transfer and the specific work, assuming the process is reversible. Process is reversible. So that means Sgen equals 0, right? So we have all the information required to find our entropy values, enthalpy values, internal energy, because both states are clearly defined. So if we go to property tables, then we can locate these states and find the required properties, right? And the question asks, find the specific heat transfer. Okay, so if you look into our delta S equation or entropy balance equation, delta S equals delta Q divided by T plus S gen, right? S gen becomes 0 because because the question says it's a reversible process. Therefore, S gen becomes 0. And this is an isothermal process. Therefore, we can write this as Q divided by T, right? So Q is equal to delta S into T. So in other words, specific heat is equal to specific entropy change into temperature. So we can write S2 minus S1 into 50 plus 273.15, right? So you can find the specific heat from entropy equation, and then you can find U1 and U2 from property tables. Sorry, U1 and U2 from property tables, and then you can apply first law for a closed system. Delta U equals Q minus W. So you can find Q from our entropy equation. So you plug in the numbers for Q from here, and then you plug in the numbers for internal energy from here. Therefore, you can find W. Okay, let's look into the solution process. So we find internal energy and entropy for state 1, and again internal energy and entropy for state 2, and from the entropy balance equation you get here. So there's no entropy generation. That's why you don't see the SGen component in this equation. So from this one, you can find the temperature. You can find the heat transfer, specific heat transfer, and then you plug in those heat transfer numbers and the internal energy values in the final answer to come up with the specific work. Any questions in this solution process? Or are we clear about the process that we followed? Perfect. So again, another reminder, we cannot use this simplification, right? So we cannot use this simplification if the temperature was not constant, right? It was an isothermal process. That's why we use this relationship, okay? And this is and this entropy generation and everything, this was the internal conditions, right? We use this for the process only. We did not consider the surroundings. Okay, example 6. Take 2-3 minutes and try to solve this one. Okay, so let's go through the solution process together. So it says it's a closed tank. Closed tank. Volume is, let's say at state 1 at the beginning. 1. Volume is 10 liters or 0.01 cubic meters. And then the mass is given to be 5 kilograms. So based on these two, you can find the specific volume of the system. And then the temperature at the initial condition is 25 Celsius. Now for state 2, temperature is given as 175 Celsius and specific volume at state 2 is going to be same as state 1 because the tank is not going to change its volume, right? So assuming this process is reversible, okay, so that means Sgen equals 0, right? To find the heat transfer and change in entropy. Okay, so there, looking at this tank, what can you say about the amount of work done during the process? Amount of work done during the process? Work done on the tank is 0, right? W is 0 because it's tricky. It has a heat pump in the description. Don't get misled by this unnecessary information. Whatever it is, it's providing heat to our tank, right? Therefore, no work done. And then with that, you can find internal energy U1 and U2 with the information given about the states. Once you have the U1 and U2, you can use the first law for a closed system. Delta U equals Q minus, oh no, not this Q, Q minus W. So W is 0. So we can find the heat transfer, right? We can find the heat transfer. And then here, from this one, we can say that Q equals mass into specific heat, mass into specific heat equals mass into delta U in this particular instance from this equation. From this, you can find the heat, and to find the entropy, delta S equals M into S2 minus S1. So the process is simple as that, right? So if we go to the solution process given here, so from energy equation, we can see that this component go to 0. Therefore, the heat transfer is equal to the internal energy change. To find that, you have the properties at state 1. It's a two-phase region. Therefore, the quality was found already. And then UN and U1 and S1 was found from the property tables and you see the quality. Similarly, for state 2, the properties are found here. And after finding the properties, it's just a matter of plugging the numbers, right? The solution looks longer, but it's just finding properties which you are already comfortable with, right? Finding the properties from the thermodynamic table. Okay, so any questions or everything clear? Perfect. So let's go through this one. Take 2-3 minutes and let's try to solve this one. And before you are attempting, can we use ideal gas assumptions here? Can we use ideal gas assumptions here? We can, because this is argon and inert gas, right? So we can use ideal gas assumptions. So now you know what the equations are to look into, right? Okay, so there's a rigid tank. There's a rigid tank which is 1.5 cubic meters by volume, and the mass is 1 kilogram. V equals 1.5 cubic meters, and mass is given to be 1 kilogram. And state 1, T1 equals 30 Celsius. Heat is then transferred to the argon. Then we heat it from a furnace operating at 1300 Celsius, so that the argon reaches okay, the entropy change during the process is given to be 0.343 kilojoules per Kelvin kilogram, right? So now we have a state 1, and we have a state 2. And then find the total heat transfer and total entropy generated. Okay, to find the total heat transfer, what can we do? What can we do about that? We can try the first law. We can try the first law. Then if we use the first law for a closed system, delta U equals Q minus W. And what can you say about the magnitude of W? Magnitude of W is equal to 0 because there's no boundary work and there's no other means of work involved, right? Are we all in agreement up to that point? Anybody? Are we all clear there? Perfect. So for an ideal gas, we all know that delta U can be written as CV delta T or CV T2 minus T1, right? So in this equation, T1 is given, but we don't know T2, right? So we don't know T2. But if we can find the T2, then we can find the total internal energy change and therefore the heat transfer, right? So for this one, now we can think of other relationships that we can use to find the temperature difference or temperature value at the end, right? In order for us to do this, we have been provided with another parameter, entropy change. The value is given. So if we think of the options we have, if we can come up with some method to find the entropy change, a relationship between entropy change and temperature, then we'll be able to find the temperature, thereby answer the entire question, right? Now you remember, for ideal gas, look at the right side of the solution. The other side is about the preparations. So we have two relationships for calculating ideal gas entropy change. So out of these two, let's name this one the first one and name this one the second one. Out of these two, what would you like to use in this given question? Relationship 1 or 2? What would be beneficial for us? Cp naught and R are given, right? Excellent. So it's always good to use in this condition, not always. It's good to use relationship 2 in this condition. Because why? Because we know the specific volumes, right? The specific volumes are known. So V2 and V1 are known, and it's known to be equal to each other. And then temperature T1 is known, and delta S, again, that's known. So what we are interested in is finding T2, right? So if we are interested in finding T2, then we can find it using relationship 2. Why don't we use relationship 1? Because we don't have any information about the pressure of the process, right? P2 and P1, we don't have any information related to that. If we need, we can calculate and go around it. But as we have the information to use equation 2 straightforward, that saves us time. Therefore, we are going to use that relationship. And at the same time, as V2 and V1 are equal to each other, V2, natural log of V2 over V1 is going to be 0, right? Therefore, S2 minus S1 equals CV naught ln T2 over T1. This portion becomes our equation because the other part became 0. Now it's a matter of solving this expression and getting the ratio between T2 over T1. Okay, so anything not clear about getting the ratio of T2 over T1? Can anybody calculate? Can everybody calculate this ratio? Can everybody calculate this ratio? Anybody having challenges? Anything not clear? So what we did here was delta S equals CV naught natural log of T2 over T2 over T1 was the expression, because the other component, the right hand top component, the one I just circled, the one I circled in blue, that went to 0 as V2 equals V1. Natural log of 1 is 0, right? Therefore it went to 0. And now what we did was this, having this, we can divide the entire equation by CV naught, and then we become, it looks like this, CV naught, and then this cancels out. And then we take the exponent of both sides. When we take the exponent of the natural log, it becomes the component inside, so T2 over T1, and then the left hand side exponent is given here. Are we clear? Or any doubts or anything not clear? Anybody? If you can answer, that would be really nice, because we are running out of time. Then we can move ahead. Thank you, Desa. And then from this one, from this ratio, we can find the T2, right? Because T1 is known and the ratio between T2 and T1 is known. So we can find T1. And we are not interested in finding the pressures. The question answer manual, like find the pressure. In this question, we don't need the pressure. So we have the temperature. So from the first law relationship we developed in above, this one, so from this relationship, delta U equals Q. Therefore, to find the Q, we can find delta U, which is equal to CV into T2 minus T1. From that one, we can find Q, right? And again, we can find total entropy generation using entropy balance equation as seen here. Take about 1 or 2 minutes and think about the solution and let me know if you have any issues or anything not clear of how we did. Are we all clear or any doubts? Anything not clear? Are we not clear at all? So what's going on? Any feedback would be nice because then we know where we all stand, right? Okay, as we are running out of time, I'm going to move forward. So this question, it's pretty straightforward. It's just a matter of locating the entropy and marking the properties on a TS diagram. So I'm allowing you to do it. The solution is here. You can cross-check your work. You can try it at home, okay? And then we have a small theory component to cover before the end of the lecture today. How to use the entropy balance equation for an open system, right? This is very important. Bear with me. I know that you have been uh, using your brains a lot today, but bear with me until this 5 moments, right? 5 minutes, the last 5 minutes. So the entropy taken into a system can be calculated by taken in and out with the mass of a system can be calculated by mass into specific entropy. So you remember we used a similar approach to find the enthalpy taken into a system, mass into enthalpy, right? Similarly, we can multiply the mass by the specific entropy to find the total entropy taken into the system with the incoming mass or taking out of the system with the leaving mass. Are we all clear about this slide? Is it difficult? Is it difficult, this part? Okay. So now, sorry. Now, uh, for a steady state, for an open system, we can write the entropy balance equation as the total entropy of the system, entropy change of the system. And then we had the entropy change due to heat transfer. We already had that in closed systems, so we are familiar with that. And entropy generation, again, we are familiar with that. So the new component that we are going to experience in an open system is this portion, the highlighted portion, right? Entropy taken into the system minus entropy taken out of the system with the incoming and outgoing mass. So are we clear about this equation? This equation, or is it difficult to comprehend? Are we clear with this one? So this portion we already had for open systems, it's still there. And in addition to that, the blue portion we already had for closed systems. And in addition to that, in an open system, what's the difference? There's mass transfer, right? So with the incoming mass, it brings some entropy. With the leaving mass, it takes out some entropy. So we can introduce that into this equation, to entropy balance equation. Then we are here. Are we clear? Yeah, in open or closed systems, entropy is not transferred by work. So for both open or closed, it doesn't matter. Work does not have a direct impact on entropy. Okay. For steady state, the entropy change of a system is going to be 0. So if we go back, this portion becomes 0 for steady state, right? And for a steady state, when that portion becomes 0, we can reconfigure this equation, the previous equation, to look like this. It's the same equation. I prefer to use the previous equation in my calculations. That's a personal choice. You can decide to go with this one or the previous form, making the change of entropy of the system to equal 0. So it's a choice. And in a steady state system, we agreed that this equation can happen. And in a reversible adiabatic process, Sgen goes to 0. In an adiabatic process, there's no heat transfer, therefore QCV over T goes to 0. Therefore, in a steady state reversible adiabatic process, the entropy taken into the system is equal to the entropy taken out of the system by the mass, right? So when we are solving these kind of problems, we can use continuity equation, first law, and thermodynamic tables and whatnot to support our solution process, as we did in the previous example, right? So now the good news is, I know it was a hard lecture, but the good news is now you are well equipped to face your final exam. You can basically do anything that is under the thermodynamics course by now. What we will be doing in the coming class on this Friday, we will be practicing open entropy balance equation for open systems, right? So we'll practice ourselves, and there's an example question down here, and the solution is given here as well. I'm not going to go through that today, so you can try it at home, right? And in the next class, we will try more questions on applying entropy balance equation for open systems.